today we're very actually happy to have Cristian D.Batista from University of Tennessee and Oak Ridge National Laboratory to talk about his work on simulations of the different low-dimensional magnetic materials. Cristian is very well known in this field, so we're very pleased to have him today. And he actually mentioned to me earlier that all the sort of software stuff that they developed is actually going to be made public. It's already made public, and so other people can use it as well. Yeah. So today's topic is a nonperturbative semiclassical spin dynamics for ordered quantum magnet. Yeah. Okay. So Cristian, it's all yours. Yeah.
Okay, thank you very much, Pencheng, and thank you also, Tomo, for this very kind invitation. So this is my second time actually giving a talk for this series, and it's really a big pleasure to connect, to colleagues, from different places, to share basically the excitement of the work that I will describe. Actually, the work that I will describe today has been indeed inspired by many collaborations with different groups, but in particular with the neutron scattering division of Oak Ridge National Laboratory, where basically I have a joint appointment between the University of Knoxville and then the lab, and we keep collaborating, and actually a lot of the things that they will describe were inspired by these collaborations. So the work that they will be describing is actually, the first part is an introduction. It's a general introduction to things that, classical and semi-classical approaches that, you will indeed, find implemented in this SANI package that they will describe in a moment. And the second part of the talk is about some recent work that, we did in collaboration with, Hao Zhang and Shenxun Zhang. So actually, Hao is the main driver from our group. And then Andreas Lohi and Tianwei Wang from EPFL and PSI that they did all these matrix product state calculations that they will be using to compare against this new semi-classical approach. And then different experimentalists, Tao Jie from Oak Ridge, that work on this material that I will show some comparisons. Alan Sheehan from Los Alamos that worked on this Delaphosite terbium-based triangular and diphoromagnet. And Andrei Sheludev and Mengche Xu that work on this very popular now material is another triangular-lattice antiferromagnet, but that one is close to the Ising limit, so it's famous because they saw very clearly this kind of spin supersolid that was predicted years ago. And as Pencheng mentioned, right, everything that we are developing, including what I'm going to describe today, is being deployed in this SANI package. SANI is a project where we are combining efforts from computational physicists, neutron scattering experts, and people like us working on theory and modeling in order to produce packages that can be used by anyone, ranging from users of a facility to any student. And the idea is that the codes are very fast, but also very user-friendly. So one only needs normally to input the zip file of the material, and then you can do pretty much apply many different semi-classical approaches or classical approaches. So in the first part of the talk, what I will do is I will introduce these kind of classical or semi-classical approaches. These are different things, classical and semi-classical. And then I will continue mainly with semi-classical approaches because the point of this, or the main motivation of this talk today, is to introduce a non-perturbative semi-classical scheme that can be benchmarked against DMRC or matrix product states, and also against the experiment. And it actually works quite well, at least for magnets that are that have a gap in the quasi-particle spectrum. Like for instance, this is the case of this triangular-lattice antiferromagnet that exhibits a 1/3 plateau, right, when you apply magnetic field. So within the plateau phase, one gets this kind of agreement, and I'm going to discuss, what is surprising here, and what kind of physics requires the use of non-perturbative approaches, right? So in particular, this is a two-magnon resonance, right, that can only be obtained if you apply a non-perturbative scheme. Just if you do a loop expansion, or more commonly a 1/s expansion up to finite order, you will never get bound states or resonances. So let me start with this kind of a general introduction, right? So when we have a spin system, we have different alternatives. One is to use classical or semi-classical approaches. Those are the most common, so I will start with those. There are other approaches that I will mention very briefly, during the talk, like large N approaches, when one introduces a different kind of control parameter, and they are useful when you have very strong quantum fluctuations, proximities to quantum spin liquids. But today is the day of semi-classical systems, so we will be far from quantum spin liquids, but still, some phenomena of these semi-classical magnets requires non-perturbative approaches. And to understand what do we mean by a classical limit, it's important, to review a little bit how do we take the classical limit of a spin system. So the simplest one consists of, you start from spin operators, which are generators of an SU2 algebra, right? They close these commutation relations. This Levi-Civita tensor is, or symbol is the structure constant of the algebra. And then one observes the following thing, that what we have on the commutator is quadratic in S. So if we make S large, kind of classical object by, let's say we replace our spin half or our spin 1 by a big spin, then the interesting thing is that, what you have on the right-hand side of this equality is of order S, but what you have on the left-hand side is of order S squared. So to leading order in S, the operators commute. And in that case, you can basically, once the operators commute, you can simultaneously diagonalize them, and you are in the classical limit, right? So you can replace the operators with numbers. And formally, the way that is done is, by restricting the dynamics, the spin dynamics, to states that are essentially so-called coherent states. So essentially, you consider a high SY state, for instance, the eigenstate of SZ with eigenvalue S, right? That will be the state polarized along the North Pole. And then you apply simply unitary transformations, rotations, right, of these states. So you can now consider the fully polarized state in any direction of the sphere, right? So this gives you an orbit of coherent states. And, each of these coherent states can be represented with a ket, or, equally, one can take the expectation value of the 3 spin components, right? And that will give you a classical vector, a normalized vector with norm equal to S. So what this means is that we can either use like a ket representation of one of these coherent states, or we can use simply the 3 components of this classical vector that we obtain when we take the expectation value of the spin components. And that tells us that then, each ket or each coherent state is in a one-to-one correspondence with a point on the sphere, right? This normalized vector describes points on the sphere. And this sphere then is going to be the phase space of our classical limit, right? So the phase space, this is important, not the configuration space. The reason why it is two-dimensional is because there is a subgroup here of transformations, in particular the rotations about the z-axis, that will leave this ket invariant up to a phase. So that's the reason why the phase space, while the group is three-dimensional, we need 3 Euler angles to parameterize arbitrary rotations. The subgroup that leaves this ket invariant is one-dimensional, so the quotient gives you a two-dimensional manifold that is the sphere, or also the complex projective space in one, right? So which is essentially the manifold of quantum mechanical states of a 2-level system, or the manifold of one-dimensional subspaces in the complex space C2. Good. So once we have that defined in that way, then we can extend the coherent states to the lattice, right? So we when we have a lattice of spins, the coherent states are simply the direct products of these coherent states of each spin. And if we want to derive the classical equation of motion, we simply use the quantum mechanical equation of motion, that is the Heisenberg equation, and then take the expectation value on both sides on these coherent states, right? When we do that, we introduce a classical Hamiltonian that is simply obtained by taking the expectation value of the quantum mechanical Hamiltonian in these coherent states. And then if we rewrite, now this equation, we get basically the very well-known Landau Lifshitz equation of motion that tells us that the derivative of this classical vector as a function of t is simply the cross product of the vector times an effective field that is simply obtained by taking the derivative of the Hamiltonian as a function of each of the components of this classical vector. This is the well-known classical equation of motion, Landau-Lifshitz equation, that can be derived from quantum mechanics by taking the classical limit. And of course, here we can use this equation if we take the classical limit, which means we replace the original problem that was a spin 1/2 or a spin 1 by large spin is going to infinity. We are changing the problem, but we are expecting that under some conditions, our quantum mechanical problem or the dynamics of our quantum mechanical problem may be well described by this classical equation, by this classical limit. One important thing is if we minimize the energy of this classical Hamiltonian, spin Hamiltonian, then we will have that these classical vectors are pointing along some direction, one for each spin. And if we do small oscillations, so we take our classical Hamiltonian and we do small oscillations, right? Remember, now the sphere is the phase space, but now when we do small oscillations, we replace the sphere by the tangent plane. And the two angles, theta and phi, actually represent conjugate, coordinate and momenta. So we have one normal mode per spin, right? If we have a lattice of spins and there is translational invariance, the normal modes will be waves, these are the spin waves. And if we quantize the harmonic oscillators of these small oscillations Hamiltonian, we get basically quantized spin waves, which are magnons, right? That's one way of deriving spin wave theory. Another way, which is more systematic, perhaps, is to simply take the spin operators, right? The three spin operators, and now write them in terms of bilinears of Schwinger bosons. These are bosons that have two flavors, and the total number of bosons is 2s. So basically, the total number of bosons is fixed, and depending on the representation, on the value of s, the constraint is that you have different number of bosons. So if we fix the number of bosons, we fix the representation of SU2, and we can write the spin operators in this way. The moment we do this, we are bosonizing our theory. So our Hamiltonian that was a function of spin operators now is a function of bosonic operators, right? And that obey this constraint. So one way of incorporating the constraint is to eliminate one of these bosons via the so-called Holstein-Primakov transformation. So we use this constraint, to write one of the bosons, the one with flavor 0, in terms of the remaining boson with flavor 1, right? And if we replace B dagger 0 and B0 here, and here, basically we get another faithful representation of the spin operators, but now written in terms of a nonlinear function of these so-called Holstein-Primakov bosons, right? So the trick is, in that way we bosonize our Hamiltonian. We can write, now the spin Hamiltonian in terms of bosons. This Hamiltonian will contain quadratic terms in the bosons that correspond to the spin wave Hamiltonian, and then terms that are not quadratic, like cubic or quartic, that will account for the interaction. So we are trading the constraint for interactions, and then the way we treat the interactions is via a systematic expansion in 1 over s, right? That in terms of the Feynman diagrams corresponds to a loop expansion. And for you to, okay, so, and this is, one of the things that I will be discussing briefly later. But, before we move into this loop expansion and, what to do and, to account for the interactions between these magnons, it's also important to realize that, for certain problems, this standard classical limit or semi-classical approach is not adequate. Simply because, for instance, for this spin 1 problem where you have this very simple Hamiltonian, right? You have a single, easy plane anisotropy, single ion anisotropy that is easy plane. If you compute the ground state of this Hamiltonian, you can immediately see that, it's the state that has spin 0. This is a spin 1, so this is the basis for spin 1. We have 3 states in the basis. And the ground state is the SZ equals to 0 state because we are assuming that T is positive. Now, the point is that this ground state is not a coherent state of SU2. So if we take the expectation value of the spin operator, of the 3 components of the spin operator, we get 0. And remember, I told you for coherent states of SU2, the expectation value should be a vector of norm equals to S. So that means that the ground state of our problem, supposedly the state above which we want to do small oscillations, is not an SU2 coherent state. So that immediately means that we need to change basically the manifold of coherent states, because essentially what happens here is that the motional quantum mechanical state of a spin-1 system is parameterized by 4 parameters instead of 2, right? The sphere is not enough here. We need 4 real parameters, or in other words, 2 complex numbers, because 1 complex number can be eliminated via normalization and multiplication by a global phase. And this motional quantum mechanical state of a 3-level system, like a spin-1 system, is actually a coherent state, but not of SU2, but of SU3, right? SU3 is the group of special unitary transformations. So special means determinant equals to 1, acting on this 3-dimensional Hilbert space. So now we have to apply all the possible unitary transformations in this SU3 group. And the manifold of coherent states is once again, the cosine ratio between SU3 and the subgroup U2 that leaves this state invariant up to a phase, which in this case is U2. So SU3 is an 8-dimensional manifold, right? Because we have 8 generators. This one, U2, is 4-dimensional. We have 4 generators. 8 minus 4 is 4. So that's the way we arrive to this 4-dimensional manifold of coherent states. And the rest of the story is very similar. We move to the lattice. We get product states, right, of coherent states. And once again, there is a one-to-one correspondence between each coherent state, each ket, and the expectation values, but now of all the generators of SU3, right? Now we have 8 generators of SU3, so we need not only the 3 spin components, or the dipolar components, I will call them, but also the traceless symmetric tensor that we can construct, with bilinears in the spin. So those are the quadrupolar moments, right? If we are thinking physically, we have 5 components that are quadrupolar, 3 components that are bipolar, and that gives you 8 generators of SU2. And for the particular ket that I was considering before, the eigenket of SZ with eigenvalue 0, what happens is, yes, there is no net dipole moment, but there is a net quadrupolar moment, right? So that's a kind of a state that has a net quadrupole, but not a net dipole. And once again, you can use.
So how quantum effect when quantum effect become important, what actually happened to the spectra? Let's say, for example, spin a half.
Yes. So you mean how quantum effects become important in?
Yeah. In this sort of approach. Right now you're talking about spin 1 and
right now what I'm doing is I'm discussing just the classical limit, right?
Okay.
We will see precisely, when quantum effects become important, we need to move away from this classical limit.
Okay,
right?
Thank you.
Now, that said, that's an excellent question. There are some quantum effects that one can capture with this classical limit that you don't capture with the classical limit that I described before.
Okay.
Right? Correct. So for instance, on-site quantum effects that will be captured by one classical limit, but not by the other. Right.
I see.
So the important thing, the message of this part of the talk is to show you that actually there is more than one way of taking a classical limit of an n-level system.
Okay.
For a spin 1, I could use the usual classical limit that I described before, right? But I will run into a problem that I don't know how to describe this ground state, with a classical spin state, because any classical state will be the spin pointing along one direction,
right?
Right? Okay. So that's the idea. That and actually there are many classical limits. I'm showing 2 only. But just to give you an idea that there is more than one way of doing semi-classics in with n-level systems like spins.
Yeah, thank you.
You're welcome. And now you can we go back to again we compute the commutation relations of these 8 generators. I will denote them by T. And once again, we can consider a sequence in the same way for for SU2, we consider the sequence of different representations labeled by S. For SU3, we need to consider a family. There are different kinds of representations, so we consider this family of so-called completely symmetric representations, where the label M corresponds to the number of boxes in this young tableaus, right? So basically, once again, one can see that when n increases, this is quadratic in M, and this is linear in M. So again, I can take a classical limit by sending M to infinity. In other words, by sending the dimension of the representation to infinity, right? We get, again, a classical limit. So that's the standard procedure. I mean, this actually is very nicely described in this paper by Perelomov, this idea of, how to generalize classical limits. And the nice aspect for quantum magnetism is that, when you generalize the classical limit, you also generalize the classical equations of motion that are obtained in this case by taking, again, the expectation value of the derivative of the Heisenberg equation of motion for each generator of SU3, right? So now when we take the expectation value of each of these generators, we get now a component of our classical object or classical vector that describes, the spin in the classical limit. But now the difference is that, this vector has 8 components instead of 3, right? 3 are dipolar, again, the expectation value of these 3, and the other 5 are quadrupolar. So now our classical theory describes the evolution of both the dipolar and the quadrupolar components of this classical vector, right? And when we write, this classical equation of motion, what we get is that the derivative of this 8-dimensional vector as a function of time is now, again, a cross product between the 8-dimensional vector and an effective field that is the derivative of the classical Hamiltonian, again, defined in the same way as before, as a function of each component of the vector. But this cross product is now the contraction with the structure constants of the SU3 also, right? Before it was the Levi-Civita tensor, so it was the usual cross product for SU2 that leads to the Landau-Lifshitz equation. Now we generalize this cross product, and we have a more general Landau-Lifshitz equation with this other classical limit. And again, once again, I mean, one important difference between this classical limit and the previous one is that I told you that the phase space of this other classical limit is 4-dimensional. So that means that if we do small oscillations, as we did before, we have 2 pairs of coordinates and momenta, right? Because the phase space is 4-dimensional. So that means we have 2 normal modes per spin, right? So unlike, the previous case where we only had 1 normal mode per spin and we obtained spin waves, right? And now we have 2. And actually, if the system is translational invariant, normally that corresponds to one corresponds to spin waves, right? Dipolar waves, and the other one to quadrupolar waves, because remember here we also have a quadrupolar in the classical limit. So again, like in the previous case, we can describe the generators of SU2 as bilinears in Schwinger bosons with 3 flavors now, right? 0, 1, and 2. And then we can eliminate one boson through this constraint that tells us, allows us to fix the representation, right? So for instance, if we normally, for a spin 1, this M is going to be 1, right? But, now we can, do an expansion in 1 over M by eliminating this constraint, right? So we write, again, the 0 boson in terms of the remaining 2 bosons, right? 1 and 2. And now we have, again, 2 bosons. That means a pair of normal modes per spin, right? And the rest of the story is the same as with the 1 over S expansion. So we do a 1 over M expansion that accounts for the interaction terms between these collective modes that here can be quadrupolar or dipolar. So in general, I mean, if you look at the kind of Hamiltonians that you get when you bosonize the theory, right? So you can write the first, these spin operators in terms of these bosons, and then you end up with a Hamiltonian for bosons that, you can diagonalize the quadratic part that is like a generalized spin wave theory, right? Where now we have 2 modes per spin. And then, the interaction terms that are like, can be cubic terms or quartic terms that, we can represent in this way because, for instance, here we annihilate two particles and we create the third one, right? These 2 particles can be magnons or quadrupolar waves, or the other way around. These are the so-called cubic vertices. Or we can have also some interaction, quartic vortices, where we conserve the number of particles. We can also have vertices like this one that do not conserve the number of quasi-particles. So typically, one is confronted, to answer Penchane's question, one is confronted with this problem. If you want to account for quantum fluctuations, you need to include these interactions, and you can do it by performing an order-by-order expansion in 1 over square root of m, and that, in terms of Feynman diagrams, corresponds to a loop expansion. So the order of a given diagram is determined by the number of loops. For instance, this is what you get here. You have only one loop. In this diagram, we have 2 loops. So it's the next ordering, the 1 over s expansion, and so on and so forth. And there are lots of beautiful works done in the past, right? To illustrate how this loop expansion works, for many magnets, right? So this is the standard way in which we do semiclassics. But the issue is that, if for complicated systems, for complex materials, these calculations can be very tedious. There are lots of matrix elements to compute, symmetrization of vertices. So one of the ideas of this ANI project was to say, well, let's try to see if one can make this more systematic in a way that, you input, again, the zip file of the material, and then internally the code generates this Hamiltonian in the first place, and then implements loop expansion, or the technique that I'm going to describe next today, which is, instead of doing an order-by-order expansion, we can do some sort of resummation, where what we do is we restrict the Hilbert space of this, let's say, let's go to the case where we only have magnons. So we assume that we can have up to a certain number of magnons. Let's say you can have 1 or 2 magnons and no more than that. And then we fully diagonalize the Hamiltonian in that truncated Hilbert space, right? Where we allow only up to a certain number of magnons. The advantage of doing that is not an order-by-order expansion, but it includes basically diagrams with an infinite number of loops that allow to account, for instance, for the formation of two-magnon bound states or resonances that are non-perturbative effects. So that the advantage of doing this, of truncating the Hilbert space and fully diagonalizing. The other advantage is that if the maximum number of magnons is 2, then the dimension of the matrix that you need to diagonalize is the number of spins times the number of spins. So it's still a matrix, so you can still work with lattice sizes of the order of 50 spins, right? 50 by 50, so, the order of 5,000 spins, and get the results in 20 minutes, right? So, and again, you can either fully diagonalize the Hamiltonian in this restricted space, or you can apply a Lifshitz algorithm, get the ground state, and then via the continuous fraction, compute the dynamical spin trajectory. So this is the kind of methodology that I'm going to describe today. The question is if this kind of methodology is accurate, right, for describing real experiments. And hopefully you will see that the answer is yes. And moreover, it agrees also very well with DMRC calculations that, can incorporate more entanglement. So the first example that I want to mention is this example where we consider, iron iodine is a antiferromagnet, in a layered triangular system. There are multiple interactions, but the important thing is that there is a strong EC axis now, single ion anisotropy, that favors the 1 and -1 states. This is again a spin 1 system, and therefore the system becomes Ising-like to some extent, and then therefore very semiclassical. Although the system is very semiclassical, when you look at, this is the data collected by Xiao Shan when he was a student in Martin's group. He obtained this beautiful data, right? This is the dynamical spin structure factor that you can extract from inelastic neutron scattering, which is essentially the Fourier transform both in space and time of the two-spin correlator. And what they found is this kind of dispersion, right? So you see this reveals, the structure of your quasi-particles. But then when you do the usual SU2's linear spin wave theory, in the way I described before, they get something very different, right? But if instead of using the SU2 linear spin wave theory, you use the SU3 linear spin wave theory, now you get an excellent agreement between experiment and theory. And the simple reason is, as you will see in a moment, that in this problem, you have two types of modes, two types of collective modes, not one, right? Not only you have magnons, right, or quantized spin waves that will have some dispersion, but you also have a flat quadrupolar mode, right? That when they hybridize, they open this gap, right? And now, this lower band is a hybridization between the quadrupolar and the dipolar mode. So in the regions where you have less intensity, it has a stronger quadrupolar character. The regions where you have higher intensity has a stronger dipolar character. The reason is that with neutron scattering, you have a selection rule that is delta Z equals to 1 that allows you in principle to only excite dipolar excitations, but here because of the hybridization between dipolar and quadrupolar, you can also see the quadrupolar. In a more schematic picture, right, what I'm saying is something very simple. For spin 1, you can flip the spin once, right, go from 1 to 0. That will be a magnon, a single magnon. But you can also flip the spin twice, right? You can go from 1 to -1. So it's like creating two magnons on the same side, right? And of course, this kind of excitation that we will call it from now on single ion bound state has delta Z equals to 2. So in principle, one cannot see it with neutrons. But if the Hamiltonian doesn't conserve the total as Z, right, in principle, they can hybridize and becomes visible. And that is exactly what happens in this material. This single magnon mode is dispersive. This is very schematic. And then the single ion bound state or the quadrupolar excitation is flat because the Hamiltonian doesn't contain biquadratic terms, right? So we get something very flat. But then because the Hamiltonian contains terms that hybridize these two modes, a gap opens here, right? And that's the gap that you see here in the data. And again, the bright regions correspond to the regions where the mode has a strong dipolar character, the not so bright regions where it has a strong quadrupolar character. So the bottom line is here you do have two kinds of modes, quadrupolar and dipolar. They are hybridized. And moreover, you can even have bound states of two quadrupolar modes. This is what I'm trying to show here. Right? You can have, if you consider two of these, they can also form a bound state. And this bound state formation is a non-perturbative effect. It's something that if you try to capture simply with a loop expansion up to finite order, you will not get it, right? Because it's a non-perturbative effect. Moreover, if you consider the cubic vertices, you have a richer spectrum of cubic vertices because you can have, for instance, a magnon that decays into two magnons, or a magnon that emits a quadrupolar mode, or a magnon that decays into two quadrupolar modes, and so on and so forth. So if you want to attack the problem, via the usual loop expansion, it's a really heavy problem, complicated. And in particular, all these vertices, right, become relevant when you apply a magnetic field, because in a magnetic field, now this mode, right, that this two magnon bound state can go down fast as a function of magnetic field and start crossing this region. Moreover, you can have these modes entering in the continuum of lower energy modes because you split these modes, and you start observing spontaneous decay and formation of bound states that are close in energy to the single particle modes. To cut the story short, right? So this is the kind of data that Martin and Xiaoshan collected as a function of magnetic field. So this is the splitting of these single magnon modes and the single ion bound state modes as a function of field. And what happens is that eventually, they start entering in the continuum, right? And you observe decay processes, like here at 4 Tesla. But also here at 3 Tesla, there is some decay happening here, right? Again, because the mode enters in some continuum. But in addition, the 4 magnon bound state, appears down here. And clearly, this formation of a 4 magnon bound state is something that you cannot capture with one loop, or even with a two loop or any finite loop correction, right? So actually, when you do a one loop correction, you get a strong decay, right? That is not observed in the experiment. In the experiment, the decay is weaker, and the reason why the decay is weaker in the experiment is because, as I mentioned before, there is a formation of, a 4 magnon bound state, right, that is not captured by the one loop correction. However, we can capture it with this exact diagonalization in the truncated Hilbert space, And what happens precisely is the moment you turn on the vertex that leads to the formation of the four-magnon bound state, you see that the decay that you used to have before turning on that attraction, now this becomes much weaker, right? So essentially, part of the continuum goes into the formation of a four-magnon bound state, and then you see a weaker decay. So all this story to tell you that you need non-perturbative approaches in order to capture effects caused by the formation of bound states or resonances.
So the intensity ratio between your four-magnon bound state and your regular spin wave automatically comes out from the calculation?
Yes, absolutely. So you can get the intensity, and you can get also the remaining.
That's actually quite novel, right? Because even for the two-magnon, neutron scatters, knows, right? For two-magnon scattering, it's very difficult to calculate.
Right.
I see.
Right. So
it's very, very impressive. Yeah.
Exactly. So you can get the intensity, you can get the suppression of the decay. Moreover, actually, we use this technique also for for modeling a terahertz experiment by Legros and Peter Armitage in Johns Hopkins. So you can get both the energy and the intensity of it. Anyway, so the other problem where it is interesting to apply this technique, to test this technique, is the one-third plateau that appears in triangular antiferromagnets, right? So if you apply a magnetic field to a triangular, let's say Heisenberg antiferromagnet like this material, there is this one-third plateau phase where the spins are in this up-up-down phase, right? So two sublattices are up, one sublattice is down. And actually, this phase was predicted in 1991 by Andrei Chubukov and Kolosov. And it's a quantum mechanical effect. So basically, for a classical antiferromagnet, you will see simply a ramp here without any plateau. The plateau, at least for Heisenberg antiferromagnets, appears simply because of quantum fluctuations. And interestingly, the dynamics inside this plateau phase is quite interesting because, as I will argue in a moment, you get bound states and resonances. And the question is if we can model that again, using this methodology, get, the intensities of the peaks and the frequencies. And in this case, for this material, as I said, there is this plateau. So what we use is a kind of extension of the spin wave theory using a very beautiful idea by Jason Alisi, Andrei Chubukov, and Oleg Starykh, where basically the way they managed to still do spin wave theory for describing the plateau is they tune the magnetic field exactly to the classical value where you will get exactly this up-up-down phase. And then they did nonlinear spin wave theory at that point that gaps out the magnon dispersion, right? And then you can get the critical fields by checking what is the field required to close the gap, right? So there will be one upper critical field and one lower critical field, that are these two values that are obtained by the condition that the gap closes, right? And not only that approach predicts, the right size of the plateau to a good approximation, but also it predicts the spin waves, right? The magnon dispersion very well, right? So actually this is the agreement between this nonlinear spin wave theory introduced by this group and the data in this cobalt-based antiferromagnet. And this is actually the approach that we use to extract the Hamiltonian parameters. So it's an antiferromagnet with a small easy plane anisotropy, right? So delta here is 0.9. And then, the intra-layer interaction is 1.7 millivolts, and the interlayer is 5%. And actually, antiferromagnets, triangular antiferromagnets, are materials that at zero magnetic field, they are very non-classical. Actually, that's an example where you cannot apply, the semiclassical approaches fail. This is actually something that we did using a large N approach, Schwinger bosons and a large N approach. But the reason why I show this figure is because we took the Hamiltonian by fitting in the plateau phase, and then we compare against, we did this kind of non-classical large N approach, and we compare against the experiments. So you can see the comparison here and here. But, this is kind of a standard approach if you're looking for materials that are close to a spin liquid phase. You can use large N or some kind of, approach that incorporates quantum fluctuations better than the semiclassical approach, but you can still use the semiclassical approach either above the saturation field or in the plateau phase. So the motivation actually for studying antiferromagnet, triangular lattice antiferromagnets, many of you in the audience know very well. The phase diagram of the triangular lattice antiferromagnet is something like this. If you allow for second neighbor interactions J2, right, and J1, as a function of the ratio J2 over J1, you go through, first you have 120-degree ordering, something like this, for the nearest neighbor antiferromagnet. But then as you increase the second neighbor interaction, then you suppress this antiferromagnetic ordering in favor of a quantum spin liquid according to numerical results. Nobody knows exactly what kind of quantum spin liquid. There is an ongoing debate, but certainly all the numerical results indicate that there is a quantum spin liquid, and that means that all these ordered magnets, at least at zero field, they will exhibit very strong quantum fluctuations because this transition seems to be continuous, second order. So the idea is, say, well, okay, for all of these materials that will exhibit strong quantum fluctuations at zero field, we still want to extract a Hamiltonian, and one way of extracting a Hamiltonian is to apply a magnetic field and go to the plateau phase, if we can, or even above the saturation field, and fit in that region. So that's what this group from PSI did for one of the materials, the cesium. This is a family of the laphosite, compounds, all, they contain triangular lattices of ytterbium. For reasons that I will not explain in this talk, they are very Heisenberg-like, despite the fact that, this is ytterbium, right? It's a rare. And for the first one, for this cesium ytterbium selenide, this group in PSI found that, you get, besides the magnon modes that appear at low energies, there is this kind of dispersive mode inside the two-magnon continuum, right? This is, again, at 3 Tesla, so it's already in the plateau phase. And a similar thing is observed at 4 Tesla. So there is this kind of resonance, right, appearing in the continuum that, can be reproduced with matrix product states. So these are basically calculations of the dynamical structure factor using the MRG in cylinders of this length and, this circumference, from 6 to 8, and they can reproduce this resonance, right? And also by fitting the data, they can get the exchange interactions. And similarly, if you do the same for now the potassium-based compound, this is data collected by Alan Shea from Los Alamos. You also see this kind of, resonance, right, above the single magnon dispersion, right? So you can see this resonance. And, now I'm showing you not only the matrix product state result, but also what we get using this exact diagonalization in a truncated Hilbert space where we include up to 2 magnons, right? So we capture this resonance, right? And one way of understanding the origin of this 2-magnon resonance that appears inside the continuum, the 2-magnon continuum, is to go to the Ising limit, right? So in general, we have a Hamiltonian like this one. We have this uniaxial anisotropy, so we can assume that delta is very large now. So we are close to the Ising limit. And then, at a small finite field, we will have, this kind of up-down phase, right? Where two sublattices are red and one is blue. But we can flip 2 spins, right? One in the up sublattice and one in the down sublattice. And we can easily check that if we flip the 2 spins together, the energy is lower than if we flip them on sides that are separated from each other, right? So in the Ising limit, you have a very strong bound state between the 2 magnons. And actually, this guy can move around the center, right? So we have actually 6 bound states that, have different angular momenta on the lattice. Can be 0, pi, 2 pi over 3, or pi plus minus 2 pi over 3, or plus minus pi over 3. So there are 6, and these are kind of these modes that I'm showing here. And in the Ising limit, they are flat. This is very schematic. If you put XY interaction, they will become dispersive. But something else that happens as you start decreasing delta, so the XY interaction becomes stronger, is that they start entering the lowest energy 2-magnon modes. They start entering in the 2-magnon continuum. Now, this yellow 2-magnon continuum corresponds to delta Z equals to -2, right? And the 2-magnon bound state is delta Z equals to 0. So they cannot hybridize these 2-magnon bound states with this continuum. But these other ones, the high energy ones, when they enter in the continuum that has delta is equals to 0, which is this case, right? For small enough delta, they enter there. They can decay and they form a resonance. And actually, this is the origin of the resonance that we see in the Heisenberg limit, right? It's basically these original two-magnon bound state that you get in the Ising limit, that when it enters in the two-magnon continuum, it becomes a resonance. And actually, this was schematic. If I show you the actual results, right? For again, the dynamical spin structure factor that you get for different values of delta. This is close to the Ising limit. You can see here these two-magnon bound states. Remember, I told you there are 4 branches because plus minus pi over 3 and plus minus 2 pi over 3 have the same energy. So these are the two-magnon bound states that now are dispersive because delta is not very large. And you can see that there is a very good agreement between MPS and this exact diagonalization truncated Hilbert space. The agreement is still quite good, for delta equals to 2. There are some small differences, but actually the differences, I don't want to spend a lot of time. You can see all the explanation of the discrepancies in the supplementary material of this paper. They are either because of size effects that you have for cylinders, or because we are truncating and we don't have 4-magnon states, 3-magnon states. But what is remarkable is that the agreement is actually quite good, and it's still very good if we make a cut, right? We cut this kind of if we show cuts, for constant Q, right? The blue and the yellow correspond to the truncated Hilbert space approach, and then the matrix product state. So you can see this is basically comparison with the experiment, and you can see that the agreement. This is the single magnon region. This is the low energy region, and the high energies here is the two-magnon continuum and the resonance. And what is interesting is to see that the red curve, the green curve, that is the non-interacting two-magnon continuum, is actually very different from the interacting one, right? So that is interesting to see, right? So that you get a very different continuum or two-magnon continuum with or without interactions. And these are the other 2 materials that I mentioned. So this is the cesium-based material, back to the material that I mentioned before in the context of the work by the PSI group. In this material, they can extract the longitudinal part only of the dynamical structure factor with neutron scattering. And this is what you get for the longitudinal response with this truncated Hilbert space approach. And this is the matrix product state approach. So you see that, again, this is the Heisenberg point, and, you get very good agreement. And actually, this is the other material, the one that is kind of very close to the Ising limit, where you have a spin supersolid. So now, as I said, you have very sharp two-magnon bound states, right, in both approaches, both in the MPS and the truncated Hilbert space. And this is the data, right? One can see indeed that these bound states are there. And actually, by fitting the bound states, not the single magnon spectrum, we were able to refine this value of delta that, in this material, it used to be 13.5 based on the fits of the single magnon spectrum, but, it's actually 14.3 or something like that. So once again, one can show cuts and compare cuts between experiment and these 2 theoretical approaches, and the agreement is actually very good. So our next goal is to work on this sodium compound, right? The one that could be a quantum spin liquid. This is a very nice work by Peng Cheng, and actually there is ongoing work also. Other samples of the same material. We are trying to apply the same technology to extract a model Hamiltonian, because this can be really interesting. Because in principle, it could become a spin liquid at 0 magnetic field. So to summarize, let me just say that, spin systems admit more than one classical limit and more than one semi-classical approach. The best classical or semi-classical approach is the one that, of course, gives the best approximation to the exact quantum dynamics. So, depending on the problem, for iodine, I said, it's better to use the SU3, a semi-classical theory for the ones, what I described in the second part of the talk is, you use SU2. And the one nice aspect is that, we can capture now non-perturbative effects by simply, diagonalizing the interacting spin wave Hamiltonian in a truncated Hilbert space. And that, the results that we get, are in good agreement, with MPS, which is an approximation that makes completely different assumptions, right? So it has a high expressiveness because, one can increase, one can add more and more entanglement by increasing the bond dimension. But, the problem is that it's limited to cylinders, right? That, are not very big along the circumference. While, this truncated Hilbert space approach, it has a lot of interpretability. You have the same interpretability that you would have if you do an analytical calculation, because you have all the exact eigenstates and eigenvalues. And, it's much faster. We can, for a system of the order of 5,000 spins, we get this spectra that they show in 20 minutes, right? So that is a big advantage. And I will say the combined application of these two, right, gives also cross-validation. Sometimes, none of the approaches is controlled. So by comparing, right, the two results, the MPS and this truncated Hilbert space ED, when they agree, one can be confident that, both are probably giving you a reasonably good approximation to the reality. So thank you very much for your attention.
Yeah, thank you, Cristian. Yeah, very interesting talk. Yeah, I have a sort of a question concerning the up and down state. So, if you go to the up and down state, I mean, what actually controls the size of the regime where the up and down state is actually stable?
Good.
I mean, as a function of the external field. I mean, there's always a region, there's always a region of phase space as a function of a field, right? That the up and down state seem to be stable. What actually controls that?
Well, so first, the quantum fluctuations, like, the lower the spin, the bigger the range, right? So the stronger the quantum fluctuations, the bigger the size of this plateau, right? So if you go from spin 1/2 to spin 1, for instance, it will be smaller, and it will become, smaller and smaller as you increase the spin. What controls that is basically you have, in the end, is the size of the gap that is generated by these interaction terms, right? So like, so essentially what controls the size is the gap that you have in the middle of the plateau, essentially. That, is determined, the gap is determined by these interaction terms. Let me go back to this slide, right? So it's actually this kind of term, right? So when in normal ordering, you renormalize the single magnon dispersion. So it's this term that will dictate, how big is the gap, the single magnon gap. Bigger the gap, the bigger the plateau. Yeah.
Let's also imagine that if you only have one of those up and down state.
Yes.
I mean, the spin wave, has to be a collective phenomenon, right? Where your up and down are completely, coherent. If you imagine yourself as having like one single up and down state, what would you expect the signal to be? I mean, to see some sort of flat mode, or you'd expect to see some sort of also collective mode?
No, you see collective mode. So you see modes like the ones that I was showing here. So you see here you see the three branches. They are dispersed.
Right. No, I understand. But this is when the up and down are really coherent, right? Let's imagine if you have some sort of incoherent up and down state. You have individual up and down that are not connected. What do you expect to see?
That will happen, for instance, if delta is very large, right? So if you have the Ising limit, then they will be very flat, right? So
I see. In the Ising limit, then you'd expect to see simply a flat mode.
Of enlarging the size of the plateau, right? So if you make delta big, so very Ising-like, of course, the plateau will become bigger. Correct? And the gap will be bigger as well. And, this dispersion will become smaller. So you have flatter bands, right?
Oh, so so how many modes would you expect to see in terms of energy?
Three, because you have a sublattice, you have a 3 sublattice order, right? So you have 3 modes.
I see.
And here the doubling comes from the fact that, you have, 2 layers. So
in this particular material.
Unit cell, right? So, but,
right.
Single layer, it will be only 3 modes. Yes.
Okay.
For this material, you have 2 layers in the unit cell, so that's the reason why you see this doubling.
Right.
The single layer, you will see only 3 modes. Yes.
Okay, very interesting. Yeah.
Right. So remember the rule, right? We have 1 collective mode per spin. If there are 3 spins in the unit cell, you will see 3.
Yeah. That makes sense. Yeah. Okay. Any other question from the audience? I mean, this is extremely powerful, right? This really goes beyond the your classical, I mean, Heisenberg and local moment type of Hamiltonian, right? It really spell out both the one magnon scattering and also two and three magnon scattering, right? In your, I mean, in neutron scattering people, we never believe two and three magnon scattering to the first order approximation because we think you never see it, right? But now you can show, you actually can see this and you can calculate it, right? That's actually very, very impressive.
Body effect, right, including resonances and bound states. Resonances and bound states are non-perturbative effects. So, we cannot get those effects with any finite loop expansion. So really the big message here is, through this kind of non-perturbative approach, we can get those effects, and those can renormalize the spectrum heavily, right? So because now you have peaks,
Right. Also, you mentioned near the end that along, close to 1 millivolt, you said that there's also a longitudinal mode, right? In the two, I mean, has that actually been,
actually they appear in the longitudinal channel because these two-magnon bound states.
Right. Has that been ever shown? I mean, because you can do, in principle, neutron polarization analysis, right? Try to see whether this is really the mode that is, what we call longitudinal mode is, Jeff Lin would know the best, right? Basically, something that, will be only, propagating along the direction of the moment, right? Has that been shown by anybody?
So this material, cesium, this particular material.
It's ordered, right? I know it's ordered, right?
It's ordered, and it has a very different G factor along the Z direction versus the in plane.
Okay.
The Z direction is very small. So that's the reason why they can easily extract the longitudinal component.
But it has not been proven that this is really longitudinal, right? From experimental perspective.
Okay. Yeah, so this is something that is happening in the longitudinal channel because remember it's delta Z equals to 0.
Okay.
Right, mode. So it's a two-magnon bound state. What I was saying here, right? So these two-magnon bound states, have delta Z equals to 0. They appear in the longitudinal channel.
Right. Okay.
And
I can comment on that. I mean, we saw a longitudinal mode in this sodium manganese material that with Stephen Wilson and Rebecca Dali, and we did polarized beam to show that it was longitudinal in nature.
Okay.
An additional mode in the system.
I see. Yeah, it's very interesting. I mean, it's very difficult to see longitudinal mode in the insulator, right? These are very good insulators. I mean, I would just completely disobey what Heisenberg is saying, right? Yeah.
Yes. Actually, these longitudinal modes, they become very strong also in the near the Ising limit, where you have strong quantum. I mean, in this kind of super solid phase, you have strong quantum effects there. A lot of the intensity comes from the longitudinal channel because essentially because of this Vanier, I mean, you have a lot of ground states there. So there is a lot of structure in the longitudinal part of the spectrum, but that's another example of something that is very quantum mechanical.
Yeah. Okay.
Here is more like, all the interesting things that can happen in the longitudinal channel also, just at the semi-classical level.
Yeah. Okay. Yes. I mean, if there's more question, yeah. Thank you very, very much, Cristian. Yeah.
Oh, thank you. And let me say finally that again everything will be available on the SANIC package. We're working on that, so hopefully in a few months.
Let us know. I'm sure many people, at least people in my group, will be very interested in using this program.
Yeah, that's our goal, to empower the experimentalists.
Yeah. Thank you so much. Yeah.
Thank you.
Yeah. Okay. Bye.
Bye. Thank you.